So what we're doing here is going over some problems, some old AP type of problems that utilize the concept, or at least test the concept of limiting reagent with some equilibrium sprinkled in. These types of questions really would be helpful if you use the concept or the stoichiometry table. Again, you may not need this table, but what I'm trying to do is give you this tool so you can see these problems as the easy problems that they really are. Okay, so I've got a reaction here, okay, and I've got something called an equilibrium constant. And as you may or may not know, Kc is equivalent to essentially something called Kp or Keq. These are equilibrium constants, and what they essentially tell us is a value of which products or reactants are favored at equilibrium. Generally speaking, they're the concentration of the products over the concentration of the reactants to their respective coefficients as their powers. But essentially, they're products over reactants. Yes, solids and liquids don't apply, but for right now, we're utilizing that concept. Now, what do we know? Well, I like to think of equilibrium as this kind of U-shaped kind of graph that I draw for many types of thermodynamic process. And that equilibrium's at low position. I can write Keq here. Now, when I draw these, right here would be 100% of my reactants, and this would be 100% of my products when I draw these. Now, you may say, well, gosh, that means equilibrium position, which you notice is the lowest position. Reactions work what? Thermodynamically are favored to always go toward equilibrium. So if you got a lot more reactants, you go toward it. If you have a lot more products, you go in the reverse, and that's Le Chatelier's principle, essentially. But essentially, this Keq position is not really in the middle. In fact, it favors either more products at equilibrium or reactants. So very simply, if the products are being favored, this position is over here, and that would look something maybe like this. Okay, that this is the 50% line, so there's more what? Products, and here's reactants. If there's more products favored at the equilibrium position, you have a higher what? Numerator that drives up your Keq. And if you've got a greater number of reactants that are favored, and that would look something probably like this. This would be my equilibrium position here. Here's 100% reactants, 100% products. What does that mean? Well, that means that there is a lot more reactants at equilibrium. Okay, so that means that your number with a lot more reactants, a higher denominator makes a what? Lower Keq value. So knowing the value of my Keq value, or my equilibrium constant, this position, tells me something about the, at least it tells me something about who's favored equilibrium, but it also tells me about how well the reaction is going to completion, and I'll explain that. So let's get back to this. So if I look at, all right, if I look at this Keq here, or this Kc, and again, Kc is an equilibrium constant with concentrations. Kp would be if you're using partial pressures, but they're essentially the same thing. It's a value that demonstrates who's favored. Now, in this case, the Keq, Kc, or Kp, in this case, it's Kc, is pretty darn big. That's very big. What does that tell me? There's a lot more products than reactants at equilibrium. I'm in this scenario here. So what does that tell me? Well, to get to a position when there's a lot more products, doesn't this reaction really have to go forward, or at least to the right a lot? And that's really important. So we know right away that with a high level of products, the only way to get a lot of products is this reaction is forced to go really one way. So this little hint right here is screaming to you that this reaction is more or less going to completion. If you have a very high Keq, and this is a pretty big one, that means you have a tremendous amount of products as compared to reactants. This number is going up, and this value here is pretty darn small in comparison, to the point where you may say it's totally going to the right. Probably is not. There's some reversibility, but not very much. So with that in mind, I can do this problem. So let's draw or look at our question here. A 1.0 mole sample of X and a 1 mole sample of Q are introduced into an evacuated, important, rigid 10-liter container. Allowed to reach equilibrium, which we know better is really completion because a lot more products are favored, according to the equation above. Which of the following is true about the concentration of the gases? Okay, well, let's draw a little stoichiometry box, and that's what this really lecture is about, using this box or this table that might help you organize your thoughts. So I have my X as my reactant, I have my Q, and then I have my R, which is a product, and then I have my Z. And what I'm going to draw is an ice table. This is my initial concentration. Here's my change, and this is the end, or at equilibrium, however you want to think about it. Now I'm going to add, okay, a number here that reminds me there's 1x for every 2 Q's, for every 1 R to 1 Z, and this is the arrow, products, reactants. Why do I do that? Because this stoichiometric ratio is really helpful to know. 2 Q's with 1 X make this happen. Okay, so what's my initial concentration? I have 1 mole sample of X, and by the way, only moles go in my stoich table here. Because it's a ratio table, a ratio of how many, you have to be in a unit of how many, and that's what mole was based upon. Gram is a mole is essentially a value that tells me how heavy. Okay, so I have 1 mole here, and Q has 1 mole. All right, very good. And because we were emptying it to an evacuated rigid container, that means that this guy has 0. All right, that's what we're doing here. Now, what happens in the reaction? Well, we're going to use up some reactants. These guys are going to go down, so there's going to be a negative change for these guys, and these guys should go up. You're going to make some. In fact, in this reaction, you're going to make a lot because you're going forward a lot because of the large Kc. Now, what is that change? Well, let's look at our ratios, and here's the first thing. We're going to find our limiting reagent using this little chart. I'm in moles. Now, look at this. In order for Q to be the limiting reagent, look at this ratio. Okay, it's 2 to 1. There has to be half the amount of Q available to make, half the amount of X available in order for all of Q to disappear. Look what I have here, 1 to 1. So because of this 2 to 1, I can see what's half of 2. And why am I saying half? Because here's 2, here's 1. It's a 2 to 1 ratio. So X, for it to work, there has to be half the amount of Q. Well, Q, I have 1 mole. Do I have at least a half of 1? Yeah, I have more than enough here. So this is my excess chemical, and this is my limiting reagent. Now, if you don't like the way I thought about that, go in the reverse. In order to get rid of all of X, which is 1 mole, you would need what? Twice the amount, because it's a 1 to 2 ratio. You would need twice the amount. So I would need 2 moles. Since I have 1 mole of X, I would need 2 moles of Q to make all of X disappear. I do not have enough, so therefore X doesn't disappear. It's the excess chemical. All right, so Q is the limiting reagent because, again, I need half its value, 2 to 1, and I have more than a half. So I have enough to drive Q away. So we're going to be minusing 0.15. Now why? Because these are going to react to make. And I'm going to, not going to minus them. I'm going to minus 1 because it's all going to get used, right? So this is going to be minus 1. It's the limiting reagent. It's going to go away. So this becomes a 0. And the limiting reagent will always go to 0. Here I'm going to minus 0.5. Why? Because it's a what? Stoichiometric relationship. X is half the number needed for Q. So if I have 1 mole, I need half 0.5. So only 0.5 gets used. So what's the end product here? Well, 1 minus 0.5 is 0.5 is available. Notice we're out of the limiting reagent. The limiting reagent stops the reaction and limits it because you run out of the reactant. In this case, we're going to assume we're going to completion or very close to that because of the large K. Now, what happens to the other side? Well, look at the ratio, 1 to 1. So as much as I lose here is the same that I gain. So this is plus 0.5, plus 0.5. And since we started with 0 because it was evacuated in the beginning, 0.5 plus 0, put that in your calculator, you get 0.5 at the end, moles, and 0.5 at the end. So look at our answers. R can't be half of Q. That doesn't make any sense. If you look at your choices, R equals Z, right? So where's my R? R value equals Z, right? And Z is greater than Q. And Z is certainly 0.5 bigger than 0, and that's why C is the answer. Okay, notice D, they're not all equal because the limiting reagent goes to 0. All right, so that's how we do that. Let's continue on the fun. And now I have a new reaction. Okay, they're giving me now the equilibrium constant to be 14.5. Now this is not very big or very small. It's about 1 or close to 1, which means in my U-shaped diagram, this dot is essentially, which is KEQ, in the middle. This is 100% what? Reactants, 100% products. So I'm pretty close. This means that there's a lot of reversibility. It doesn't really favor more than another, but it does tell me there is some reversibility. It does go back and forth, and that's important. So let's do the problem. Well, they give me 1 mole sample of carbon monoxide, a sample of H2, my 2 reactants. They're pumped into a previously evacuated reaction. There's nothing there. Which of the following is true at equilibrium? Okay, fine. So we have what? We have CO, we have H2, and we have our CH3OH. We have our stoichiometric relationships. There's 1 of these, right? Nothing in front implies 1. 2 here, and nothing in front implies 1. And here's my initial change, and at the end. Now let's see what it says. How much do we have? We have 1 mole sample of CO, so there's my 1. Remember, it has to be in mole. Grams would not work here. 1 mole of H2. And because it was pumped into a previously evacuated or empty container, we have nothing of the product yet. So if you think about my U2, I'm starting where? I'm starting with a lot of reactants, and it's going to be very spontaneously work this way. Okay? Let's just say, since we don't know how forward it's going to stop somewhere in the middle, but let's just say we know there's 0 products, right? So we know the products are going to increase. But let's just say, for instance, let's just pretend we're going to go to completion. What would happen? So let's pretend we go forward to the right, and I'll explain why this works. All right, so the first thing is find limiting reagent. Oh, here we go again, 2 to 1. So for this to be the equilibrium, since it's 2 to 1, the CO has to be half as much, right? 1/2, 1 to 2. So this is a 1 to 2 ratio. So in order for H2 to totally disappear and lose 1 mole, I have to have half that amount here. Well, what's half of 1? 0.5. Isn't this at least 0.5? It's 0.5 or bigger. Yeah. So this is my limiting reagent. And we would lose, again, 0.5. And this would go to 0 because it's limiting. Okay, limiting reagent's going to always go to 0, assuming we have what? Well, assuming we go to completion, but we're going to do that for a reason here. 1 minus 0.5 is going to give me 0.5 left over. And of course, this is a 1 to 1. This lost 0.5. This has to be what? Gaining a positive 0.5. Add that to 0. And at the end, I have positive 0.5. Trying to. So, party people, this is what I have. Assuming I have what? I have a completion reaction. Now, because the KEQ is close to 1 in the middle, we're not going to be in this position all the way up here, 100% products, or at least somewhere in between, right? We're gonna move backwards somewhat. So we can expect what? CH3 to the product to go down, and the reactant what? Well, the reactants, which are over here, are to go up a little bit. Don't know how much, right? We assumed we're going to completion, and that's exactly what we would have if we ran out. But we know the KEQ is in the middle somewhere, and we're saying it's about 14.5. So at equilibrium, this is not truly a completion reaction. We're going to go backwards a little bit. So we pretended we went to completion, and now I'm just going to move backwards somewhat. And again, I'm just doing some estimates here, but bottom line is the amount of product won't be 0.5 because it's going to move backwards a little bit, and the amount of the limiting reagent won't be 0 in this case because you're going to make more as the reaction moves toward equilibrium. You should learn you always move toward equilibrium, so the reverse reaction is going to be spontaneous. And of course, CO2 will increase also, so the reactants will increase. So look at your choices. H2 equals 2 CO2. Well, there's no way that this will be equal to 2 times CO2, okay? Not going to work, all right, because this is going to be a bigger value. H2 is smaller than CO2. H2 is definitely smaller than CO2. I like that, right? Because you're going to be at 0, it's going to increase the same amount. Well, actually, this is going to double the amount, but essentially, I'm going to believe that H2 is smaller. Now, people love C. CO, this guy, are equal. People like to think that these are equal. Now, I only have these numbers equal to each other when we're at what? A completion reaction with a very, very high KQ. With a lower KQ like we have here, as I said, it's going to go backwards, so this is going to be smaller than this. So in truth, CH3, okay, is going to be, cannot equal, right? CO cannot equal CH3. They would if it was completion. This is going to go down a little bit. This is going to increase. So that's why I get rid of these guys. That's the reason. There's no way that 2 times CO would equal H2. Okay? It doesn't work quite like that. So this is the best choice, B. H2, okay, is going to be smaller. Why is it smaller? Because it was limiting, so it lost more in its 1 mole than the CO. Okay? So that's why B is the best answer. All right, so number 3, moving on here. All right, in the reaction, what is the total number of moles of reactants consumed when 1 mole of CO2 is produced? So this is a little different. So they want to know the total number of moles of reactants. So I have C3H8, I have my O2, and they're talking about CO2. I don't need water in this case, right? It's a relationship between the mole fractions or the mole relationships in front. So there's 1 here, there's 5 here, and there's 3 here. Okay, I don't need water to do this. Here's my ice table. And let's see what we have here. Now, 1 mole of CO2 is produced at the end. How much is needed in the beginning? Well, look at the reaction. I have propane plus oxygen. What is this? This is combustion. And you should know combustion or burning, the KEQ is extremely large. How do I know? There's no equilibrium when you burn. We never see a house burning and it's reached equilibrium and stops. Okay, it keeps going until you run out of the fuel, usually in this case the propane. All right, so these are tremendously completion reactions you should be aware of. So if I'm going to have a completion reaction, I'm going to start with some amount of my reactants and have 0 products. To go from 0 to 1 at the end, it must have been a +1. Look at this. This is a 3. This is a 1. So that could be a 1/3 of a mole, if this is a mole. And this is a 1 to 5. If this is 1/3, what's 5 times? Well, this could be 5/3. Now you could use fractions if you want, but 5/3, okay, is the 5 to 3 ratio of the 1 here. However we want to think about it. So 1 to 5, so I times this by 5, it's 5/3. Or if I times 5/3 to 1, I get the same thing. Okay? And of course, that's going to be the change. Okay? And what do you have here? We do not know what the initial values are, but we have the change. That's clearly the change. This is -1/3 minus. You're losing it to make the products. What were they asking? The total number of moles of reactants consumed. That's changed. I'm looking for the total at the end. Okay, so I know I lost or consumed 1/3, and I also lost 5/3. And you can do this percentage-wise if you want. But what's 5/3 plus 1/3? And you got it. You get 1/3 plus 5/3. You get 6/3, which is equal to 2. And that's why the answer is choice D. The chart really helps. Okay, and again, if you do this with percentages, it won't come out as nice, but it certainly will be the closest answer to 2. And you say, well, how do we do percentages? Well, how do I go from a 3 to 5 ratio? Okay, well, you take your 1, okay, and again, you times it by 5/3. And of course, that gives me 5/3, but you can do 1 times 5 divided by 3 and get some fraction. This fraction would be 1/3 of it, or some decimal, and you go from there. I don't have to find the end. I don't have to know the initial. They wanted what was consumed, which is the same thing as changed. Okay, and that's why D is the answer. Okay, 4. They don't bring up any equilibrium here, so I can assume what? That I am in a what? A scenario where I am pushing this forward, okay, to completion. This is a redox reaction, and most redox reactions are either working or not. So here we go. Here's my permanganate ion, MnO4, and here's my C2O4 -2. And we have what? How many moles of CO2 involved? I just need the ratios of the chemicals involved. And if I look at my coefficients, there's 2 of these, per 5 of these, per 10 of these. Okay, here comes my ice table. What's the question state? How many moles of CO2 are produced, that's over here at the end, when 20 milliliters of an acidified 0.2 molar solution is added to 50 milliliters? This is we're going to do a stoich problem with solutions. This box requires moles. So I got to take my solution and make moles. Well, how do I do that? Well, molarity is equal to mole over liter. So liter times molarity gives me moles. How does that work? Well, molarity is mole over liter times liter. You can see what cancels, you get your moles. So let's do that. So we need moles, and the molarity formula helps us get there. So let's do that math. Very simple. Again, all we're going to do is multiply liter times molarity to get moles, because we're going to cancel the liters. So if I look at my first value for the permanganate ion, I have 20 milliliters. That's the same thing as 0.020 liters. And I'm going to times that by the molarity, which is the concentration. Now notice the K in front. That just means the K comes off and gives you the permanganate ion. And that's going to be what? 0.20 moles over the liter. That's what molarity means. And look what we have here. Okay, so 0.2 times 0.02 is going to be 0.004 moles. Okay, and if I do the next one of the oxalate ion, or oxalate ion, and sodium front's going to go away because the sodium is what? Very, very soluble, group 1 ion. So I take my 50 milliliters, which becomes what? 0.050 liters. I'm going to times that by my 0.1 molar, okay, which is really 0.10 moles for every liter. And we can see what cancels. Liter goes bye-bye. And 0.05 times 0.1 gives me 0.005 moles. All right, so now that I'm in moles, I can use my stoich table. And initially the permanganate ion, okay, which was this 20 milliliters and 0.2, gave me 0.004 moles. And the oxalate ion is 0.005 moles. Okay, now they said that in the beginning we have no information regarding the CO2, so we're going to assume we're going to start a reaction with these reactants with the protons available, and this will be 0. Okay. Now, the first step in the process is to find my limiting reagent. So it's a 5-to-2 ratio. So what does that mean? Okay, well that means that in order for all of the C2O4 to disappear, I need to have at least 2/5, 2 over 5, 2/5 of the 0.05. 2/5, how do I do that math? Well, I can definitely divide by or find that value, but wait a minute, 0.005, what's a fifth of 0.005? Well, a fifth of that is 0.001. So 2/5, okay, 2/5, right? We're doing the ratio here. It's 2/5 of that would be 0.002. So my friends, it's 0.002 that you're going to lose. The question is, do I have enough of the permanganate ion to make all of this disappear? And the answer is yes. I need 2/5, right? And I have more than enough. So I know that this is my limiting reagent, and therefore I'm going to lose all of it. Okay, it's going to go to 0. This goes to 0.002. And what happens here? Well, what are they asking for? Okay, what is in the balance? How many moles of CO2? That's what they're asking. Well, I know this is a 10:5 ratio, right? What does that mean? The products are double than the reactant in this case, 10:5. There's twice the many particles. So if it's minus 0.05, this is plus 0.010. And we're going to assume we didn't have any, so that is how much I produce. And that's why we pick choice D. Now, I know I did all of this other work just in case they asked for how much is remaining and who is the limiting reagent, but you had to know who the limiting reagent was in order to figure out this problem. I believe this chart method helps you think things through. Easy for me to say. Now, we could have done this another way, okay? And let me show you. And this is important. This is the tie-in for tonight's lecture. Okay, I can do this mathematically using my dimensional analysis. So let's start with 20 milliliters, 20.0 milliliters of my MnO4 negative ion. That's KMnO4, that the K comes off when it dissolves. All right, NO4, and it should be negative. Okay. Now the first step is that I am going to get rid of my milliliters to go to liters. Say, why am I doing that? Well, because I want to use molarity, and I'll explain. Okay, just watch here. I'm going to get rid of my milliliters. I'm going to divide by 1,000 milliliters equals 1 liter. So now that I have liters, the next step is I'm going to use the molarity of the permanganate ion, which is 0.2. Now what does that mean? There is 0.2 moles per 1 liter. So party people, you can see what I just did here. By converting to liters and then using the molarity, I'm getting the moles of my permanganate ion. Isn't that what we just did? Yeah, but we're just doing it all in one step. Next step, party people, we're going to get rid of the permanganate ion. Here comes the stoichiometry. And there is what? There is 2 of these per how many oxalate ions? Okay, C2O4, negative 2. And that goes bye-bye. And now I have moles of this. But we want to convert that back into what? Milliliters. Just like we did on the first page of this worksheet, but now we're using molarity. So I got moles. All right, well, I want mole to go on the bottom. And I want to convert it to liters. What's the molarity? Oh, it's 0.1 molar for the oxalate ion. So there's 0.1 moles per 1 liter. And now I have liters. And the next step is to convert to milliliters. For every 1 liter, there's 1,000 milliliters. And look what we just did, party people. We used what? The molarity in 2 different places in my stoichiometry problem to go from the moles, go from volume to moles, and now moles back to volume. So we were using the molarity of the oxalate ion here because it canceled out the potassium permanganate. And we used the molarity of the permanganate ion here because we still had it. Let's go find that number. So when I put this in my calculator, 20 times 1 divided by 1,000 times 0.2 times 5 divided by 2 times 1 divided by 0.1 times 1,000, I get 100 milliliters of my oxalate ion. So what this says, if given, and if I have 20 milliliters of this permanganate ion in this concentration, I need 100 milliliters to make it all go away. Do I have 100 milliliters of my oxalate ion? No. I only have what? 50 milliliters. I do not have enough. Therefore, the oxalate ion is the excess. Or I should say, I do not have enough oxalate ion to make the permanganate all disappear. This is my excess, right? And this is my limiting reagent, okay? And that's what we have here. So certainly you could have done all of that math to come up with that end result there. A lot of work, okay? And if certainly you can go the other way as well. Interesting enough, notice that 100 milliliters is needed for oxalic acid, and we didn't quite have enough, okay? We only had enough to do what? 0.02. I would need double what we have to make all of the 0.4 go away. Well, hello, we had 50. Double that would be, hey, it all kind of makes sense sometimes. So in any case, this last little bit I showed you because I want you to be able to do stoichiometry with molarities. And that's what the next part of this is. Hope that helped.